Okay, so let's take a look at chapter 3, processes. So processes are a very important concept, and we'll cover what exactly a process is in the operating system context. Right? We'll describe how we use processes in operating systems. They are very prominent in scheduling, multitasking, and keeping the computer running efficiently. Right? We'll do a little bit on interprocess communication, and then we'll describe a little bit about how these work in client-server systems. All right, so let's describe what a process is. Uh, in operating systems, you can have the concept of batch systems. Right? These are where jobs are introduced into the operating system for execution. It's a little bit different than how we have operations with a real-time type of computer that reacts with user keystrokes or user interaction. The more common type of system is not batch. Right? Batches typically are found in large mainframe systems, and an example of what an application would be on some of those systems would be payroll processing for millions of users in a system. Right? For timeshare systems, user programs or tasks, that's more similar to what we are familiar with laptops and computers, where we have user programs that the operating system runs, and then there are jobs associated or tasks associated with each one of those programs that we run. So a process is a program in execution. Right? A program we know we write in source code, and then we compile it to an executable form, and then when we run that program, right, we invoke that executable. We either double click on an icon, or at the command line we specify we're going to run a program which usually has an extension of exe, for example. When that program is in an execution mode, when it's running or when it's active, it instantiates a process. So you can think of a running program as a process in the operating system. And to the operating system, this running process, or this, I'm sorry, that's redundant, this running program or process has multiple parts. There is the program section or program code called the text section, where the executable logic is being processed or being run by the operating system. Where we are in that text section is tracked by the program counter. So the program counter is kind of a pointer into which line of code is being executed in that program. So if you have a 100 line program, when you compile that, that could be a 2 to 300 or 400 line assembler code or executable code. And this program counter is pointing to which line of that 2, 300, or 400 line executable code. There's a stack which contains temporary data. Right? This is work that's maybe being calculated as part of the program execution. And then there are, it can contain things like the function parameters, what those values are, the return addresses. Addresses are locations in your code. Values of local variables. These are just some examples of temporary data that would be stored in the stack. There's also a data section. This contains global variables in your executing program. And then there's also a heap structure, which contains memory that's dynamically allocated, for the program to use while it is running. So just to reiterate what a program is compared to a running program or a process is restated here. That a program file is a passive entity. It's stored on disk. When you run it and it becomes an executable, or it is an executable, that when you run it, it becomes a active process to the operating system. Okay? And you can have many active processes that you initiated. You can have multiple programs that you run at any one time. As an example, you can on your desktop have Firefox running, Notepad, any of the Microsoft Office products running all simultaneously. Each of them will have at least one active process associated with it. Some of these programs create multiple processes as part of that single executable. Microsoft Word, for instance, fires off multiple processes that are all running as part of Microsoft Word. Okay, so let's move on. When a process is in memory, this is RAM on the hardware side, the operating system uses that RAM to store different parts of a program or the process that is running, and allows for this information to be used by the CPU. Remember from the earlier chapters that the CPU only interacts with RAM. It only interacts with memory. So memory is where the information gets presented to the CPU to do work, to do calculations, to receive data, and then the CPU in turn does its processing and then exchanges or outputs the results of that back into RAM. So this is a physical representation of what the RAM contains when a process is in it or when a program is executing. So the top part of memory is max. That's the max memory. It might be 4 gig, it might be 10 gig of RAM that you may have on your computer, for instance. It starts at 0 and goes up to, say, 4 or 10 gig, whatever multiple of storage that you have. So there's that text section that's being used by the operating system for a running program or a process. There's a data section, the heap we talked about, and then this is essentially free memory, and then we have a stack. So this is all how it's represented in RAM for an executing program or a process. Process state is an important concept. A process moves through different states throughout its time that it is active. It is not all the time being used by the CPU. And a lot of this is because we want to keep the CPU busy. So a process that's active may have reasons to be swapped out, may have reasons to have a lower priority than all of the other processes that are also waiting to be waiting to get time with the CPU. So as a result of that, we switch context in each of these active processes. So just by definition here, when a process executes, it goes through these various state changes multiple times in some cases, right? When the process is first created, right, when it gets first executed, the state associated with that process is new. Another way to say that is that the state of that process is new. When that process actually gets time on the CPU, it is considered in the running state. So we change the state of that process from new to running. When the process is waiting for some event, okay, so it's not on the CPU, it's not running, then we have that as a waiting state. It'll be in the ready state when it is waiting to be assigned to a processor to do work. And of course, when it is on that processor, on that CPU, then it would be in the running state. Right? Then when the process completes, it is considered terminated. Once it becomes terminated, it's no longer active, it's no longer doing anything, so the process or no longer is important and it isn't tracked anymore by the operating system. The operating system essentially is only being taking inventory of the different process states for the active processes. So don't confuse an active process with running, because an active process are all the things that are currently being handled by the operating system, but not all of them are taking up time with the CPU. Only for a single CPU computer, only one process is actually running at a time. Only one process is active and running on a CPU at any point in time. Everything else, every other active process, would be either in one of these other states. Okay, so that's an important thing to understand. In this diagram, we're showing the relationship between these different states in the process and how you get from one to another. So once again, when a process is newly executed, it has the state of new. It then will transition from that state into the ready. It'll go from new to ready by the activity or transition of being admitted. So now it's in the ready state. It can move out of the ready state in only one way. It'll move from the ready state into the running once the scheduler dispatches it. So this is the only path that a process goes from new. It can only go to ready, and then from ready it can go to running. Now once it's in running, we see that there are these three exit paths. From running, it can go to I/O, via I/O into a waiting state, or it can go from running to ready if it gets interrupted. So this arrow indicates the action. It can also go from running into terminated if the process has completed. When it's in these different states, you follow the arrows and the action associated with it to see what the possible subsequent states are. And as we said before, when a process is terminated, it has completed and it's no longer needed to be tracked or have any relationship to the operating system. It's done. We don't care about it until it becomes executed again, and then it'll start here on the new. Next, let's take a look at the process control block. This is how the operating system tracks the information for all of the active processes. So at any one time, there could be hundreds of active processes. Some of these processes are from user programs. So like I was saying earlier, it could be a process for Firefox, for Word, for any user-initiated program. But there are plenty of other processes that the operating system itself will run and that are part of the running operating system. So for each one of these active processes, the operating system maintains this process control block information. These are unique and assigned to every single active process. Right? So if we come back here, and we follow this flow. This flow is the roadmap for all of the active processes. So it goes from new to ready to running. Perhaps from running, it terminates and exits completely. Or it'll go to a waiting and then ready and back to running. Right? So while it's doing all those state changes, the operating system maintains this for each of the active processes. Right? If there are 100 active processes in the operating system, it would have 100 of these process control blocks in order to maintain that information for each one. So there's a process control block that the operating system associates and tracks for every single active process. So let's go over what some of these data items in the PCB relate to. First one's easy. What is the process state? And it makes sense that the operating system must maintain that. So a new process is created. The process state in that case is new. Program counter, right? We spoke about this briefly. This is where we are in the program being executed. What line of program code, if you will, the pointer is associating to. The CPU registers, these are local storage, right, associated with the process. The CPU scheduling information about priorities and queues could also be in there, right? And then there's memory management information. What is the limit? How much of that RAM is being used by this process? And some additional I/O and accounting information. So it's everything that the operating system needs to track for an active process. And the reason that it's tracking this information is it's important to the operating system so it knows what to do with a given process. And it makes decisions on priority and on scheduling based on the information in this process control block. Now let's look at an example of how these process control blocks are being operated on or being used in the physical sense by an operating system, right? So here we're showing a data structure of a linked list for each process control block. So if we look here on this first part, we have a ready queue. Right? So these are all of the processes that are waiting essentially for the CPU. When they get the CPU, if you go back to that state diagram, then that process is in the running state. All of the processes here, we have two that are shown in this linked list. These are all in the ready state. So we have process control block for process number 7, process control block for process number 2, and all of the associated information for each one of those processes is stored in its respective process control block. So with this data structure, as a linked list is tracking or storing, is the information for these two processes that are in the ready state, right? This is a representation of I/O devices, but we would have a similar ready queue or a similar data structure for all of the processes that are in the waiting state, for example. There would only be one process that is in the running state, so there's no need to have a data structure per se in that example. But for the ready and the waiting, you certainly would. So how does the operating system determine which process to take off of the ready queue and give it to the CPU, right? In other words, how does the operating system decide of all of the items on the ready queue to assign or give to the CPU? So we would have our ready queue shown in this box here. in that previous slide, there are two processes in here, right? So it'll put one of those two. It'll decide from that which one gets the CPU. So that would it would pick I think process 7 or process number 2 in some manner, right? It could be by priority, it could be by uh, order it was placed in the queue. So maybe it just takes the first one off the top of the queue and gives it to the CPU. When it's doing that, obviously it will change the state of that process. Say it picked process 2, it'll change that state of that from ready to running, and then it'll allot it some time. If it completes, then this flow here would show that it terminated and it is exiting. So the state would change from running into terminated. But if it's not completed, then it could possibly have one of these four flows. It could have the running process could have initiated an IO request, then it would go into an IO queue, so it would wait in here for the IO to actually execute. Once that IO did execute, then it would go back into the ready queue and get CPU. This flow is necessary because I/O is a very, very slow operation. You don't want to have that waiting take place on the CPU. So anytime a process is in the CPU and it needs an I/O operation, we immediately remove it from the running state. In other words, we take it off of the CPU and put it into this request flow for I/O. This takes a long time. You don't want that sitting on the CPU and then everything else that's waiting on the ready queue is unnecessarily waiting for a very long I/O operation. Instead, what we do is when there's an I/O, when there's a request for I/O, it comes off the CPU and it follows this flow. That way, we free up the CPU to take work from the ready and do something else. So while the CPU is busy, that I/O flow is now happening in parallel and waiting, and it waits for the I/O. This operation for I/O is several thousand times slower than the CPU. So by removing it in this flow, we potentially allow for 1,000 other processes to get time with the CPU. So this is a very important concept in managing the resource of the CPU to keep it busy. If there's any time that it needs to wait for I/O, you remove it and then continue processing the other things in the ready queue. You could also execute or exit the CPU not for I/O, but because your time on the CPU expired. We don't let processes run to the very end without any regard to time. Perhaps what we do on the CPU is say that you get 5 or 10 or some number of CPU operations, and after which time, if you're not completed, you'll just come down into this flow where your time expired. Maybe you need 30 cycles of the CPU and you get 10 at a time. So you may have to go through this flow 3 times. And once again, the reason you do that is so that we can be fair about getting time with the CPU. So your time could have expired. You got 10 cycles of the 30 that you needed to run, and then you'll come into this flow and you'll wait here and then get back onto the ready queue. Right? You could also fork a child process, which is a sub-process, and then wait for that to execute and then go back into the ready queue. Lastly, it could be an interrupt operation, which also takes you off the CPU and puts you into this flow so that we can allow the computer to do some interrupt operations, and then you go back into the ready process, into the ready queue. So these are all 4 examples of ways that we remove executing or running processes off the CPU to put them into this alternate flow so that the CPU stays busy. Each time we switch from one state to another, that's considered a context switch. Context switch is important for the operating system to do, as we've explained. It's done to keep the CPU busy and to work the ready queue. If you've got 1,000 active processes, you don't want any one process to hog up the CPU and have the other 999 processes wait. They will be waiting, but what you want to do is try to get a little bit of work done for each one of those processes, as opposed to spending 1,000 cycles on just one. So it's a bit of trying to work the line in a more efficient manner while keeping the CPU busy. Now, when a CPU switches from one process to another, there's some overhead associated with that context switch. Right? So the operating system must save the state, and this is where all that information goes into the process control block. So it saves that so that we remove that process off of the CPU into a save state, and then we bring on the new process for execution. Right? So saving that process control block information during the context switch is one of the most important things that you use the PCB for. Right? So it is overhead, but it's a necessary overhead in order to multitask the CPU to run and keep it busy at all times.